Hello everyone. In this lecture we will try to use the generalized Coulomb's law to fish out the concept of the scalar electric potential. Then this will give us a relationship between the electric field and the scalar electric potential. Then we can use that to recast the Gauss law into a form which involves the potential instead of the electric field. And this will give us two equations. One is known as the Poisson's equation, and a special case of that will be the Laplace equation. And this Laplace equation ultimately forms the basis for the solution of the Laplace equation. Will give us the potential that we are looking for in various physical scenarios. So let us say I start with the generalized Coulomb's law. Okay. So this is the generalized Coulomb's law. So this generalized Coulomb's law is given as E, which is a function of the position vector r. So the electric field at some position vector r is equal to 1 by 4 pi epsilon naught times the integration of rho. Rho is the charge density, then r minus r prime divided by r minus r prime cube, and times d tau prime. So here rho and d tau prime together, that is going to give us the charge. So now instead of a volume charge density, because the volume charge density is the most general case, instead of a volume charge density, let's say we have a surface charge density, then accordingly we will have sigma, and here there is going to be a surface element. And if we have a linear charge density, then instead of rho we will have lambda here, and we will have a line element in this case. So now we will use a result in what follows here. We will use this result. The result, what it says is this. So if I take the if I find the gradient of this quantity, that is 1 by modulus of the position vector, okay, the gradient of 1 by modulus of the position vector, that is equal to minus r cap, that is a unit vector along the radial direction, divided by the modulus of r square. Okay, which of course can be written in this way, because the unit vector can be written as r by the vector r divided by the modulus r. So that is going to give us a vector r in the numerator, and that one more modulus r, that will we can absorb into this one and write it as modulus r cube. So where did we get this? How do we get this? This is one of the problems, which is exercise problem, which is given in Griffiths. If you are interested, then maybe we could just I'll just quickly walk you through how we obtain this. So let's say I consider Cartesian coordinates. So in Cartesian coordinates we have r, the position vector r is equal to I cap into x plus j cap into y plus k cap into z. So which gives the modulus r is equal to under root x square plus y square plus z square. So therefore, if I want to find out the gradient of this quantity, now of course this is a scalar, so the reciprocal of this will also be a scalar. So the gradient of 1 by modulus r is equal to the gradient of x square plus y square plus z square to the power minus half. Okay, so now we need to just differentiate this. We need to differentiate this because that's what a gradient does. You do the partial differentiation with respect to x, multiply with I cap, then partial differentiation with respect to y, multiply with j cap, partial differentiation with respect to z, multiply with k cap. So that's what you do when you're trying to find out the gradient. So now when I try to differentiate this with respect to x, then we can use the chain rule. So first you differentiate the outer function, so minus half is there, so x square plus y square plus z square to the power minus 1 by 2, so minus 1 by 2 comes outside, and then x square plus y square plus z square to the power minus 1 by 2 minus 1, it gives us a minus 3 by 2. Now you differentiate the inner function. So when you differentiate the inner function with respect to x, differentiation of twice x is going to x square is going to give us twice x, and y square and z square, anyway they are I mean they are independent with respect to x, so that these differentiation of these two will give us 0. So and this entire thing, whatever after the result, whatever you obtain after differentiation, that will be has to be multiplied with I cap. So now of course this 2 and this 2 will get cancelled out. Okay, and of course the same thing will happen when you do a partial differentiation with respect to y and with respect to z, which actually I am not writing here. I mean, we can just infer what will be the other expressions from here. Just replace. Okay, so I instead of I will get a j cap, and over here this will remain unchanged, and here we will get a y for the y component, and for z we will get a k cap, and here we will get a z. So now we take this minus I cap, we take the minus I cap, and then this x we take it over here, and this quantity, because there is a minus here, so we just write it down. We write it as x square plus y square plus z square to the power 3 by 2. So now we see here that this can be written, this what exactly is this quantity? So x square plus y square plus z square to the power 1 by 2 is modulus r, right? X square plus y square plus z square to the power 1 by 2, or root over that is equal to modulus r. So this quantity is basically modulus r cube, because there is a 3 here, so this is modulus r cube. So essentially what we have here is minus I cap into x by modulus r cube. Similarly, the next term will get minus j cap into y by modulus r cube, minus k cap into z divided by modulus r cube. So I can take minus common outside, and then modulus r cube also common in the denominator. So what is left behind is I cap x plus j cap y plus k cap z, which is nothing but the r, the vector r. So the gradient of 1 by modulus r is equal to minus vector r divided by modulus r cube. So now I could take one of this modulus r from here, because this is cube, so we could write this as modulus r square into modulus r. Then that single modulus r we could take it up into the numerator, and when we take it to the numerator, so we have a r by modulus r, so that is going to give us the unit vector. So that's why we are able to show that this is indeed the case. Okay, so we are going to use this result here, and how we use this result is we will just replace r with r minus r prime. Now if you recall, this r is a unprimed coordinate, and r prime is a prime coordinate. R prime is what is used to refer to the positions of the source, that is the charges, and r is used to refer to the positions of the field. So if I have 1 by r minus r prime, now I am doing a divergence, simply a nebula here without any prime. That means I am trying to differentiate, because after all, sorry, not divergence, gradient. So after all, gradient is nothing but a differentiation with respect to position. So we are doing a differentiation with respect to position over here. And which position vector are we trying to differentiate? We are trying to differentiate with respect to r, not with respect to r prime. So when you do that, then we can just borrow this result from here. So gradient of, I just replace, instead of modulus r, we replace with modulus r minus r prime, and this will be equal to minus, write down this one, minus, in the numerator we have this vector, separation vector, which is r minus r prime, and in the denominator we have modulus r minus r prime whole cube. So we're going to use this result, because now you can see in the generalized Coulomb's law we have r minus r prime divided by modulus r minus r prime whole cube, which is this quantity. So that means we can replace this. We can replace this with minus, because there is a minus sign involved. So this quantity can be replaced with minus gradient of 1 by r minus r prime. So that's exactly what you're going to do here. So this modulus r minus r prime divided by r minus r prime divided by modulus r minus r prime whole cube is equal to minus gradient of 1 by modulus r minus r prime. Let's call this equation number 2, with equation number 1 being the generalized Coulomb's law. So now all you need to do is just use equation number 2 in equation number 1. So when you use equation number 2 in equation number 1, like I had mentioned some time ago, so this will get replaced with gradient of 1 by modulus r minus r prime. Now this you're trying to differentiate here. So now we need to bring some perspective here. What are you trying to differentiate? Because we are having two things. We are having an integration and we are having a differentiation. So we need to get some clarity here as to the integration is done with respect to which variable, and the differentiation is done with respect to which variable. So there are two variables here, two position vectors. So one is r and another one is r prime, right? So this r is the vector with respect to which, this r is the vector with respect to which we are performing this differentiation. Okay, we are performing this differentiation with respect to r, and with this r prime with respect to this vector we are performing the integration. So the integration is with respect to r prime and the differentiation is with respect to r. So keeping this in mind, because r and r prime, they are independent of each other, because it really does not matter. You could have this field point anywhere, at which point you would like to measure the field, that is independent of where the charges are kept. So r and r prime, they are independent of each other. So because they are independent of each other, so I could just move around. There is no reason that first I have to differentiate and then I have to integrate. I could do vice versa also. So first I could do the integration part and then I could do the differentiation part. So I take the gradient outside the integral. So we take the gradient outside. So we have this. Now I could just take this rho and then place it here. So rho r prime d tau prime divided by r minus r prime, and this integral is what I am trying to find the gradient of. Now we can as well, because it's a constant, we might as well take this also inside. And what we have here is this. Finally, we just keep the minus sign outside. Barring the minus sign, everything else we take it inside. So minus gradient 1 by 4 pi epsilon naught, then this integral. So this is what we get, and this is equation number 3. Now if you look at the quantity that is inside the brackets, okay, if you look at the quantity which is inside the bracket, so this quantity is a scalar quantity. You can see here, this is a constant, rho is a scalar, this is a volume, you are taking the volume integration of rho by r minus r prime. This is also a scalar. So you are taking the volume integral of a scalar quantity. So this is going to give us a scalar field. So what we have here inside the bracket is basically a scalar field. Okay. So this means that we can write down the electric field. The electric field can be written as minus gradient of some scalar field. Okay. The electric field can be written as the negative gradient of some scalar field. And this scalar field we just represent, we call this as phi. This entire scalar, this whatever quantity we have inside the brackets, I write this as phi. And this phi, what will it depend on? It will depend only on r. How do you know that this is going to depend only on r? Because it has r prime also. The reason is we are integrating with respect to r prime, because you see there is a d tau prime. This is a volume element, the volume in the source, right? So we are integrating with respect to r prime. So any variable that you integrate, that the result of the integration, it becomes independent of that variable. So it becomes independent of r prime. So the only variable that is going to remain is going to be r. So phi, this quantity we call it as phi. So this phi depends only on r. So the electric field can be written as a negative gradient of some phi, and this phi is what we call as the scalar electric potential. So this is the scalar electric potential, the familiar scalar electric potential. This is how you find it. So now once we get the scalar electric potential, so we can go ahead and we can obtain the curl of the electric field. So what is the curl of the electric field? So if I want to find out the curl of the electric field, so what you do is you take curl of the electric field, I replace it with minus grad phi. So curl of minus grad phi. And this one, of course, I take the minus sign outside. So we have minus curl of grad phi. Here it was curl of minus grad phi. So take the minus outside. So we have curl of minus curl of grad phi. And this is going to turn out to be 0. Why is this 0? Because the curl of the gradient of any scalar field is always going to be 0. Okay. So this is if you could just refer to Griffiths 4th edition, section 1.2, page number 23, the equation 1.44. It says exactly the same thing. The curl of the gradient, the curl of a gradient is always 0. So there you have it. We have found out the curl of electric field. So now we can say what is the we could just summarize this. So we already know that the divergence of the electric field, right? So the divergence of the electric field. So what is the divergence of the electric field? We know from Gauss law, the divergence of the electric field is rho by epsilon naught. And now we have found out the curl of the electric field also. The curl of the electric field is not electric field, electrostatic field. Let me be clear about this, because in general the curl of the electric field is not 0. Only in case of stationary charges we have this. So the divergence of the electrostatic field is rho by epsilon naught, and the curl of the electrostatic field is 0. Okay. So if we know the divergence and if we know the curl of a vector field, we can in fact find out, we can completely describe that same vector field. So there you have it, the divergence and the curl of the vector field, which is the electric field E. Okay. Next, we find out, we try to relate the work done. Okay, the work done, we try to have some energy considerations and how to relate this to this quantity which we have just defined, that is the electric potential, okay, the electric potential which I have just defined, how do we relate it to the energy of the system? So suppose I have a point charge with Q which is taken from point A to point B in an external electric field. So let's say these are the lines of force, these are electric lines of force, okay, and then we have in this region we have some point A and some point B. There is some charge Q, and this charge Q I am taking it from point A to point B along some arbitrary path. Okay, so let's say when the charge is over here, it has from here it undergoes an infinitesimal displacement dl, and at this point the electric field is E as shown in the diagram. Then at any point on the path, the electric force on the charge is obviously charge times the electric field, because all you need to know is the electric field. Once you know the electric field, just multiply the electric field with the charge, and that is going to give us the force which is experienced by this charge. So the force is equal to Q into E. So then if I want to move this, obviously this path that is shown here, the path that is shown here, that is not going to be the path which is going to be followed by the charge if you just leave it alone, leave it only at the mercy of the electric field. Obviously the charge cannot move like this. The charge is going to move along the line of force, right? But if we want the charge to move along this path, then that means we have to apply some external force. That means there will be some external work which is going to be done in moving the charge from point A to point B. And this external work done, to do this external work, we have to apply an external force, and this external force has to be at least equal to the negative of this electric force. That is, it must be at least equal to minus QE. Why exactly, what is the reasoning behind this? If you would like to know, then you can refer to one of my recent lectures for the undergraduate level, where I have discussed this in detail. So once that is established, then we can find out what is the work done, and work done is nothing but force dot displacement. Only in this case is the force has to be minus F, because it's an external force, okay, the work done by the external force. So minus F dot dl, and then what is F? F is equal to QE, so minus Q integration E dot dl. Okay, so now what we have is electric field. We saw the electric field can be written in terms as a negative gradient of some scalar field, and that scalar field happens to be the scalar electric potential. So what we do is we express this electric field in terms of the scalar potential, that is some minus gradient of some scalar potential phi. So we have minus Q integration from A to B minus gradient phi dot dl. So this minus and minus will get cancelled, and then we will get Q into integration from A to B gradient phi dot dl, and this is going to turn out to be Q times the value whenever we integrate this. This is from the fundamental theorem of gradients, fundamental law of gradients. Whenever we try to do something like this, this is just like all you need to do is whenever you are trying to integrate, find the line integral of the gradient of a scalar field, that is same as finding the value of the gradient, finding the value of the scalar field at the two boundary points, that is at B and at point A, and just taking the difference between the two. And how we get this result, for then again I would like to refer to you to Griffiths in section 1.3.3, which is on page number 30. You could refer to this result, that is known as the fundamental theorem for gradients, which basically says the same thing. That is, whenever you are trying to find the line integral of the gradient of a scalar field, then that will be equal to the evaluating the values of the scalar fields at the two boundary points A and B. These are two boundary points. It's a curve, so one end is A, another end is B. So obviously you are finding out the value of the field at these two boundary points. So T at B minus T at A. So here instead of T we are having phi. So that's how we get this result. So Q into phi, of course, is going to give us the electrostatic potential energy. So this equation above, it tells us that the work done, because ultimately what we have here, this is work done. So if you look at it, left hand side we have the work done by the external force, the external work done, that is equal to Q into potential at point B minus Q into potential at point A. Q charge times potential is the potential energy. So that means this quantity Q into phi at B is the potential energy at point B. Q into phi A, which is the potential at energy at point A. So that means the external work done will be equal to the difference in the electrostatic potential energy. So which is a very satisfying result, because it is similar to what we are used to in, let's say, the gravitational case. Whenever we have a central force, gravity is a central force, we have a similar result over there also. Now the Coulomb force is also a central force, so we expect something similar like this. So this is a result which is expected. Okay. So now this gives us to the Poisson's equation. So what is the Poisson's equation? Poisson's equation is basically nothing but the Gauss law. The Gauss law, which is recast with respect to phi. Okay. Instead of E. Now the Gauss law, we all know the Gauss law, it gives us a relationship between the electric field and the charge distribution. Now we recast the Gauss law. Instead of electric field, we recast it using the scalar electric potential. So that is going to give us what is known as the Poisson's equation. So the differential form of the Gauss law, which we had discussed in one of the previous lectures, the differential form of the Gauss law is divergence of E is equal to rho by epsilon naught, which is equation number 1. Then it's just 2 steps. The electric potential is, in terms of electric potential, the electric field is E equal to minus gradient of phi. Oops, sorry, my mistake. Let me correct this. Okay, so this should not have been divergence, it should be gradient, which has been corrected now. So in terms of the electric potential, the electric field is given as this. So now you can guess the next step. All you need to do is just replace, insert equation number 2 in equation number 1. So when you do that, using equation 2 in equation number 1, so we have divergence of E, and this E I replace it with minus grad phi. So divergence of minus grad phi is equal to rho by epsilon naught. So divergence of gradient will give us the Laplacian, and this minus sign I take it on to the other side. So the Laplacian of phi is equal to minus rho by epsilon naught. So this equation above, which is known as the Poisson's equation. So this also gives us a special case of this is the Laplace equation. So what is the Laplace equation? It is simply the Poisson's equation in charge-free regions. That is, in charge-free regions, rho is going to become equal to 0. So it means the Laplacian of phi is equal to 0. And in most cases, where we have some kind of a distribution, we are interested in finding out the electric potential and the electric field in some region which is free from any other charges. So in most of the cases where there is already some kind of a distribution, and that distribution is producing some kind of electric potential and consequently electric field, then generally it is the Laplace equation which is what we solve. So let us say, so this is the Laplace equation. The Laplacian of phi is equal to 0. So now the Laplacian equation will just we'd like to obtain some kind of an insight into what kind of how does the solution of the Laplace equation, how does it actually behave. Okay, we'd like to obtain some kind of insights into this. So the first we'll start in the simplest case, that is the Laplace equation in one dimension. So in one dimension, this Laplacian is going to simply become the total derivative, so second total derivative of phi with respect to x. And this we see it is basically an ODE, right? So this is an ordinary differential equation. So now this ordinary differential equation can be actually solved, because this gives us this is basically telling that the second derivative of the function is 0, and we already know that the general solution in such cases is a function like this. And you can notice here, you can just try out this solution. First derivative is going to give us m, because m is a constant, b is a constant. When you differentiate it once with respect to x, b is going, the differentiation of this is going to become 0. Differentiation of this is going to give us m is a constant. Differentiate once again, then that differentiation of that constant m, that is also going to give us 0. So we'll get this. So this is a general solution, and by looking at this, we know that this is actually a linear solution. So moment I see something like this, the second derivative of the function is 0, so we immediately know that the solution is a linear solution. Okay. So now the values of this m and b, how do we find out the values? To find these values, we need to know the boundary conditions. So this is where the boundary conditions come in. So there are two features of this solution that we should always keep in mind. The actual values of m and b, they are going to be set by the boundary conditions, but there are two features which is going to be same for all scenario. So this is how the solution would look like. Okay, as you can see here, general solution is this. So it should be a linear solution. So here I am assuming that the slope is positive, but you might have as well have a scenario where the slope is negative. So we have a scenario like this. So we have a straight line, okay, the phi along the y-axis we have phi, along the x-axis we have x, and then the variation of phi with respect to x, it's going to be a straight line variation. So there are two features which gives us insight about the behavior of the solution. The first feature is that because it's a linear solution, we immediately know in case of linear solutions, the value of the function at any point will be equal to the average of two values on either side, two equidistant values. So let's say I want to find out what is the value of the potential at point x. Okay, so without actually knowing the value of the potential at point x, suppose I know what is the value of the potential at x minus a and x plus a, I could use these values, the value of the potential at x minus a and the value of the potential at x plus a. All I need to do is just find out the average values, average of this value and this value, that is going to give us this value. So phi is the average of the this phi at x minus a and at x plus a, and this average, how do you find out? Very straightforward, because the number, this is a boundary point and this is another boundary point, so two boundary points, so 1 by 2 times this value plus this value, so which is going to give us some value in the middle, and because it's a straight line, this is going to be the exact value that we are looking for. So phi is the average. Okay, so how do we generalize this statement that I have written here? The generalization is the phi at any point is equal to the average of the values of phi at the boundary points, because you can see here it's a one-dimensional case, so it's a straight line and only the x-axis is there, so the boundary will be 2 points for a line segment. For in the one-dimensional case, the boundary points are two different points. So all we need to do is find out the value of the potential at the boundary points and take the average. Okay, so find out the average of the potential at the boundary points. So that is going to give us the value of the function at the midpoint. So this is what we need to keep in mind. That's the first point. And the second point is, you see it's a straight line. The function is the solution is a straight line, and in a straight line we know that the maxima and minima for a straight line function, the maximum and minima. So suppose I consider a region here. Okay, this is the region which I consider. Then we know that if it's a straight line, if it's a straight line fit, then the maxima and minima can only take place at the boundaries. You cannot have, in case of a straight line, you cannot have a scenario where there is a local maximum at the middle or there is a local minimum somewhere in the middle, because if the function, if it increases to a local maximum, then it has to decrease. Okay, so that is not possible. You cannot have local maxima or you cannot have local minimum. Okay, if it has to be a straight line function, the extreme values, that is the minimum and the maximum values, they have to occur only at the endpoints, only at the boundaries. There cannot be any local maxima or minima. Okay, so this is the feature. Okay, so these, as we will see, these two features will also be valid not just in the one-dimensional case, they will also be valid in general in the two-dimensional as well as the three-dimensional case. So let's look at how the Laplace equation behaves, what's the behavior of the solution of the Laplace equation in the two-dimensional case. So in the two-dimensional case, this is what the Laplacian turns out to be. Okay, it is not this one is not an ordinary differential equation. This is a partial differential equation. Okay, so this is a partial differential equation, which means that the particular solution of this partial differential equation is determined by the boundary conditions. Okay, so just like previously, so here you can just imagine, so in the one-dimensional case it was a straight line. In the two-dimensional case we will have a surface. Okay, in one-dimensional case we had a straight line, two-dimensional case we have a surface, and this surface that we have, it is going to follow it's going to have two features which are very similar to these two. The first feature says that the value of the potential at any point is the average of the values in the boundaries. Okay, in a boundary which surrounds that particular point, and the extremum, they exist only at the endpoints. There cannot be any local maxima or minima. So taking these two ideas forward, so we could have a scenario which looks like this. Okay, so we have here this x-axis and y-axis, and then potential along the along the vertical z-axis. So we have some surface. So this is the potential is going to vary as per this surface. Okay, and then suppose I want to find out the potential at some point xy. So how do you find out the potential at some point xy? So what we do is we consider a circle. Okay, a circle which surrounds this xy, circle of certain radius which surrounds this point x and y, and then we find out the value of this potential at each and every point on this circle. Okay, the value of the potential at each and every point on this circle. Okay, then all we need to do is just find out the average value of each of these 5 values on this circle. That average value is going to give us the value of the function over here. So that is the first feature, okay, which I have noted down over here. So that's the first feature. This phi at xy is the average of the values on a circle about the point xy, and we could write it. And the second one is that all the extrema, they can occur only at the boundaries. Okay, just like before, there cannot be any local maxima or minima. There can only be the extrema, they can occur only at the boundaries. So here the average, okay, I had forgotten to mention this over here. Let me just write this down here. How will this look like? The phi at x comma y, the value of phi at x comma y, it is going to be the average. So 1 by 2 pi r times, you have to integrate over the entire boundary. The boundary is going to be a closed loop, the integration of phi dl. So this is what the value of this potential at this point xy, this is what it's going to look like. So these are the two features of the solution. Then finally we come to the Laplace equation in 3 dimensions. So in Laplace equation in 3 dimensions, that's the full form, which is Laplacian of phi is equal to 0. So Laplacian of phi equal to 0. Now it is difficult for me to make a visualization like this. Here it was easy because it's just one dimension. The second dimension gave us the potential. Here 2 dimensions are there. The third dimension gave us the potential again. But if we consider 3 dimensions, x, y and z, so in that case, how do we visualize the potential? So one way to visualize the potential is I could use some kind of a color code, which of course is difficult for me to put forward in the form of a diagram. But we can still arrive at the 2 features. What kind of solutions we will get, we can still arrive at them. It will be just the same as this. Okay, the same features will be applicable here also. So the particular solution in this case, because this is also a partial differential equation, the particular solution, it is determined by the boundary conditions, and this will also have 2 features. And what are those 2 features? The first feature is that the value of phi at some point r, it is the average of the values on a spherical surface of radius r, which is centered at this same point r. And how do you find out the average? This is the way you find out the average value of the potential. So instead of a circle, we have to consider a sphere. Okay, we have to consider a sphere, and this sphere, the boundary of this sphere is going to be a spherical surface. So we need to find out the average value of phi on this spherical surface. So that's the first feature, which you can see here progressively. It is basically the extension of the first feature in the 1D case and the 2-dimensional case. This is an extension of the first feature. And the last feature is going to be exactly the same as before. All the extrema, they occur at the boundaries. There are no local minima or maxima. So that is your Laplace equation in 1-dimensional, 2-dimensional, 3-dimensional. So this gives us this brief analysis. It gives us a feel for what could be the behavior of the Laplace equation. So suppose you get the solution to the Laplace equation, whether your solution is valid or not, you can actually test it very easily by trying out if it satisfies these 2 features. If it does, for instance, if you find a solution, let's say you do a solution and you find that in the region in which you have considered the Laplace equation, the solution of the Laplace equation, it gives us a local maximum. So that means there is something wrong with your solution, because you cannot have local maxima in the solution for the Laplace equation. So there is somewhere where you have gone wrong. So you can actually do a course correction after that point of time. And finally, we have what is called as the uniqueness theorems. There are 2 uniqueness theorems, the first and the second uniqueness theorems. I will not be going into the details of this of the derivation of this uniqueness theorem. This derivation is available in Griffiths. I'll provide the references. So what is the first uniqueness theorem? I mean, these are very useful theorems. What does the uniqueness theorem say? It says that the solution of the Laplace equation in some volume. So let's say I have some volume. I want to find out what is the potential inside this volume. That means I want to know, because what is the Laplace equation? The Laplace equation is the Laplacian of phi is equal to 0. If we solve this, we will get phi. That means we will get the potential. So I want to find out the potential inside some volume. Okay, so I want to find out the potential within some volume. So how do you find out the potential within some volume? To find the potential within some volume, all I need to do is I need to know the potential on the surface. So if I know the potential on the boundary surface, I can uniquely find the potential inside this volume. Okay, so that means if the boundary is given and if I am able to find a solution which satisfies this boundary condition, then the first uniqueness theorem, it guarantees that the solution which I got, that itself is the correct solution. Okay, so it really does not matter how you obtain the solution, by hook or crook, any way you obtain the solution, as long as that solution satisfies the boundary condition, then you know that your solution is correct. Then there is a corollary to it, and the corollary is the potential in a volume, the potential phi in a volume is uniquely determined if the charge density in the region and the value of phi on all the boundaries, if these are satisfied, if these are specified. Then the second uniqueness theorem, again, instead of the second uniqueness theorem, the first uniqueness theorem, it gives us the potential. The second uniqueness theorem, it gives us the electric field. Okay, so what it says is this: if I have some volume, okay, if I have some volume and this volume is filled with some charge density, some specific charge density, then the electric field in this volume is determined uniquely if I know, and let's say there are some conductors inside this conductor, this is one conductor, this is another conductor, this is another conductor, this is another conductor. So we have many different conductors inside this volume. Then suppose inside this volume there is also some charge density rho. Then I want to find out what is the electric field in this region. Then all I need to do is I need to know what is the total charge on each of these conductors. And if I know the total charge on each of these conductors, I can uniquely find the electric field. Again, this proof of these two uniqueness theorems you can find out in Griffiths. So I'd like to refer to you the uniqueness theorems in Griffiths. There is in section 3.1.5, which is on page number 119. I'm talking about the 4th edition of Griffiths. And then I had mentioned some time ago that it really does not matter how you obtain the potential. Okay, as long as the potential satisfies the boundary condition, that has to be the correct potential. The first uniqueness theorem, it guarantees that. And one good way, a very excellent example of this is what is called as the method of images. I would again refer you to Griffiths section 3.2.1 in page number 124. There are a couple of really interesting problems, example problems. You could go through these and that is going to give you a better understanding. And then I'm keeping some reading assignment for you. One is known as a separation of variables, using a separation of variables technique. I mean, the method of images need not be applicable under all circumstances. The method of images, you can apply it only if there is some kind of symmetry in the system. So in that case, you can exploit the symmetry to quickly find out the potential, okay, using the method of images, but that is not always possible. Okay, it is not possible that the system may always have some kind of symmetry. So in that case, of course, we have to find some analytical way of finding the solution of the Laplace equation. So one very common way, one very popular way is known as the separation of variables, very robust method of finding this the solution. So I'd like to refer you to again Griffiths section 3.3, which is on page number 130 on this one. And then generalization of this, the Laplace equation in the spherical polar coordinates, that leads to another interesting result which can also be very easily applied to problems just by looking at the kind of solution that you are looking at. Just by looking at the geometry of the problem, you could actually use the Laplace equation in spherical polar coordinates. Okay, so please I'd recommend that you refer to these sections, and that will complete the understanding of this particular topic. So with this, we come to the end of this lecture. Thank you.